what he was expecting. But this changed his relation with mathematics, and from that time he went into research in strong way and very fast way, actually, solving two strong conjectures, Reed conjectures, and then together with Eric Katz and Karim Adiparisito, they solved the Rato conjecture. Maybe the strong idea was more than solving the conjecture by itself, but using different tools of mathematics, tools where the conjecture didn't seem to deal with. And this is probably something that can characterize the work of June, working on different aspects of mathematics, getting together different ways of thinking on mathematics. Mainly geometry, but with topological tools, using singularity theory, tropical geometry, matroids, etc. So today we'll have a talk on Lefschetz theorem and Hodge-Riemann for finite geometries. Thank you, John.
Hey, thank you for the kind introduction. It's a huge honor for me to be able to be here and to be able to speak to you. So thanks for having me and thanks for coming. And I also feel very fortunate because the things that I'm going to talk about is heavily motivated by the work of Lefschetz, as you can see from the title of the talk. And I heard that there's a very tight connection between Lefschetz and the Mathematical Society at Mexico. So this may be a good opportunity to promote some recent advances on the basic ideas coming from Lefschetz's work on topology of projective complex varieties. So the title says, I'll say something about Lefschetz and Hodge-Riemann relations for finite geometries. But I don't want to start my talk by telling you what Lefschetz and Hodge-Riemann is, because I want to push all the technical statements to the very end of my talk and wait until most of you become unconscious. But let me just emphasize my point of view on this Lefschetz and Hodge-Riemann. So these are certain statements that were originally discovered by Lefschetz and Hodge and their collaborators that are supposed to be true for cohomology of Kähler varieties. So originally this started as a statement on complex manifold theory or the theory of projective complex varieties. But during the last 50 years, we have discovered that there are many Lefschetz type theorems concerning various type of mathematical objects and not just Kähler manifolds. For example, now we have a statement that we now call Lefschetz that are valid for all convex polytope. And we also have Lefschetz theorem for all Coxeter groups. We also have Lefschetz theorem for matroids. And we also have Lefschetz theorem, conjectured Lefschetz theorem for algebraic cycles on projective varieties. This is part of the standard conjecture. And same goes for the Hodge-Riemann relations too. So these statements, Lefschetz and Hodge-Riemann relation, usually comes in as a package. So if you have a mathematical object that you very much like, then there is some chance that you will be able to construct a certain cohomology-like object, an algebra maybe, which satisfies Poincare duality and Lefschetz theorem and Hodge-Riemann relations. And these three properties are modeled on those corresponding theorems that we know in algebraic geometry, for example, but they are all logically independent. For Poincare duality for polytopes, for example, that I have in mind, you can prove it, but it does not follow from the corresponding proof of the Poincare duality in topology, and same for Coxeter groups and matroids and so on. These are all independent statements that are somehow true or conjectured to be true for some reason. So this is some pattern that we see in mathematics concerning these very rigid mathematical structures. So Poincare duality usually says that if you have this cohomology-like object, which is a graded vector space, for example, then what happens in degree k and what happens in co-degree k are related. Precisely speaking, Poincare duality will say that the two vector spaces which appear in degree k and co-degree k are naturally dual to each other. Hardt-Lefschetz theorem, on the other hand, says that there is a very explicit isomorphism that can be constructed from the geometry or the given set of data that you can construct from the degree k piece to co-degree k piece. So it's a separate statement from the Poincare duality statement. Poincare duality says that the two spaces are dual to each other. Hardt-Lefschetz theorem says that the two spaces are isomorphic to each other by some explicit given isomorphism. So when you have two dual spaces that happen to be isomorphic, then you can pair the two elements using that isomorphism and define a symmetric, for example, bilinear form on the original space. That concerns the Hodge-Riemann relations, and the Hodge-Riemann relations predict that this bilinear form, say for example a symmetric one, will have some very particular signature. It predicts that you will have this many positive eigenvalues and that many negative eigenvalues. But this is just a rough form of the statements that we now call Poincare duality, Hardt-Lefschetz and Hodge-Riemann relations. And the actual content of these statements very much depend on the context. And I'm going to introduce one of these contexts, which are somehow related to those statements in algebraic geometry, but not entirely. But let me just assure you that every single statement that I'm going to say during the next 50 minutes is entirely linear algebra. And I'm not lying. So nothing more than linear algebra. So the only question, if I say something non-trivial, then the only question is this: how well do we understand linear algebra? And I'm going to formulate a version of Hardt-Lefschetz and Hodge-Riemann relations starting from a linear algebraic data. And these are conjectured to be true for any given collection of linear algebraic data that we're going to introduce. But either we don't know elementary proof of it, or we just simply don't know whether it is true or not. So I'm going to show you some of the statements, linear algebraic statements. So let me tell you first a little bit about the Hardt-Lefschetz theorem in this linear algebra context. And let me start by showing you some pictures. So let's start from a projective plane, or plane. And maybe think of the 4 general points on projective plane. What I'm going to do is to connect every pair of points by a line. So if I started with these 4 points, and then I get 6 lines. So let's remember those numbers, 4 and 6. Okay, I play this game for another configuration of 4 points, now not in general position, but maybe 3 of them are in a line. I again connect every pair of points by line, and this time I get this picture where 4 points determine 4 lines. So the numbers are 4 and 4. And let's continue and maybe start from more interesting configuration of 7 points, where I have chosen my 7 points to be all those points with 0, 1 coordinates. So I'm having in mind this homogeneous coordinates for a projective plane. So I'm thinking about points 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, and so on, and 1, 1, 1. These are my 7 points. If I play the same game, I get this picture, where 7 points determine 9 lines. And let me now do something that some algebraic geometers like to do, and which produces a pretty picture. So I'll keep the same 7 points with the same coordinates. But now what I'm going to do is to move the prime P in the base spec of Z toward the particular prime 2. What I'm doing is that we are having in mind the projected plane that are constructed by taking, that's defined over some particular field. And then I'm changing that field to have a field of some finite characteristic, in this case, approaching toward 2. And then our game will produce a different answer. So long as my characteristic of my base field is not 2, we'll basically see the same picture. But at the limit where my P hits the 2, the 3 red points are on a line at the limit. So they are collinear at infinity and produces this picture, where now 7 points determine 7 lines. So this is a picture of the final plane. Okay, so this was the result of our 4 experiment, and we clearly see one universal pattern. So there is a theorem here. And the theorem is this, right? Every set of points, E, in a projected plane determines at least cardinality E many lines. Right? This is what we have observed. And of course, there is one exceptional case where my set of points E is entirely contained in a line. Then it will determine just one line, and the statement is not true. But with that single exception, it can be proved in many different ways, and some of them purely combinatorial and elementary, that this statement is actually true for any possible configuration in the plane, as was proved by De Bruijn and Erdős in the 40s. So I claim that this is a shadow of the Hart-Lefschetz theorem. And I'm going to reveal a bit of pieces of information how this is related to Hart-Lefschetz in the context that I'm interested in. But of course, there is no reason to stop at the plane. We can play the same game, say, for example, on 3-dimensional spaces. So if I have 4 general points on 3 space, and it will determine 6 lines, just like before. Join every pair by lines. And if I join every triple by planes, then you see 4 planes. So the numbers in this case is 4, 6, 4. And if I add one more point in general position, then now I have 5 points, and it will determine 10 lines, because 5 choose 2 is 10, and everything is general position. And 5 choose 3 is 10, so 5 points determine 10 lines and 10 planes. So the numbers are 5, 10, 10. But if I move the 5th point into a slightly more special position so that it is contained in one of the planes that are already determined by the original 4 points, then the numbers change in a certain way. Now I have 5 points that determine 10 lines, just as before. So the number of lines is not affected, but the number of planes is now 7. So 3 planes are gone. So the numbers are 5, 10, 7. Or I can specialize even more so that the 5th point is now in one of the lines. Then the number is 5 and 8 and 5. So by experimenting with ever more complicated point configuration, you get variety of numbers. But still, you see one common pattern in all these numbers, 4, 6, 4, 5, 10, 10, 5, 10, 7, 5, 8, 5. So you see a theorem now, just analogous to the previous one. So actually there are 2 statements, which says that the number of planes is at least as large as number of points. And secondly, the number of lines is also at least as large as number of points. And the first statement was proved by Mutskin in the 50s, and the statement is just like the one before. Every possible set of points E in a projective space of any dimension determines at least cardinality E many hyperplanes, except in one case when E is entirely contained in a hyperplane. So this is also one linear algebraic manifestation of the Hodge-Lefschetz phenomenon. And the proof of this statement is somewhat more delicate than the previous one of the De Bruijn and Erdős, but still quite elementary and can be done in a page or two. But the original proof of Mutzkin had the interesting feature of using particular properties of the real numbers. So he had in mind this real projective space, but the theorem is true for any reasonable projective geometry. And that was achieved by Basterfield and Cowley in their 60s. Okay. So the theorem says that one number is at least as large as some other number. And the numbers in the interest is the cardinality of some sets. So it says that the cardinality of the set L1 is bounds from below the cardinality of this other set LD minus 1, where LD minus 1 is a set of hyperplanes determined by a set of points which I choose to denote L1. So one set has larger cardinality than the other set. So why is something like this true? And there is only one reason why cardinality of one finite set is larger than cardinality of some other finite set. The reason should be that there is an injective map from one set to the other, and there is no other reason. So you could hope that there's maybe some natural way of finding an injection from L1 to LD minus 1. So I'm trying to go a little bit toward the statement of the Hodge-Lefschetz theorem, which in classical setting says that there is an injective map from degree k piece of your cohomology to the co-degree k piece of your cohomology. So let me switch the language to that of linear algebra from the projective geometry. I'm going to restate everything in terms of linear algebra. So let's say I have a set E, which is a finite spanning subset of some d-dimensional vector space V. So a collection of vectors. And I assume that it spans the entire vector space. And I'm going to write L for the set of subspaces of V spanned by subsets of E. So in previous pictures, these are like set of points and set of lines and set of planes and so on. All subspaces of V spanned by subsets of E. So this set, the elements are subspaces, so I can express it as a disjoint union of various pieces, LP, where LP is the set of all p-dimensional spaces in my collection L. So this is a graded poset in the language of combinatorics. So let's just calibrate our understanding by running one simple example. So if I have 4 general vectors in all 3, then L0 is 1, because there is only one zero-dimensional subspace in my collection spanned by empty subset of E. And L1 has cardinality 4, because I have 4 general vectors. L2 is 6, because every tuple of vectors spans distinct 2-dimensional space. 4 choose 2 is 6. And L3 is 1, because every triple of points in my configuration spans the entire thing. So the numbers are 1, 4, 6, 1. And 6 is larger than 4. And the general conjecture, generalizing the earlier work of De Bruijn and Erdős and also of Mutzkin, says that for any spanning vector configuration you start in a d-dimensional vector space, the number of p-dimensional spaces that you see in the collection is at most the number of co-dimension p subspaces that you see in the collection for any possible vector configuration. And for every possible choice of p, which is at most half of d, the dimension of the entire vector space. And for example, the case of De Bruijn and Erdős rule corresponds to the case when d equals 3 and p equals 1. And as a result of a Hodge-Lefschetz theorem that I'm going to discuss later, we can now prove that a somewhat stronger statement, but somewhat more natural statement. So we can prove that for every p at most d half, there is an injective map from the set of p-dimensional spaces to the set of codimension p spaces, but not any injective map, but the one that preserves the instance relations between the subspaces. So I'm going to produce an injective map, but this map will have extra property that it sends a subspace X to a subspace that contains X for all X. So it respects the process structure of L. Yes?
This map, is it natural with respect to the action of making linear maps? So if I take some points, I apply a linear transformation. Is it equivalent with respect to action of linear maps?
So, I mean, one of the subtle points in proving statements like this is that, in fact, there is no canonical choice of these injective maps. There is a whole lot of them, and this is one of the reasons why it's so hard to prove that there is one of them, at least one. And this is just like somewhat like the case in the geometry. If you want to prove Hodge-Lefschetz with respect to a fixed Keller class, this is somewhat challenging, and it can be done. But the point of the Hodge-Lefschetz is that it's a statement really about family. There is a distinguished, given any, for example, projective or Keller manifold, there is a cone of positive classes in the degree 1 or 2 part of cohomology with respect to which Hodge-Lefschetz is true for every possible choice of Keller form or ample class and so on. So the possible value choices of these injective maps corresponds to that ambiguity. And the whole point is you should try to prove construct all these reasonable injective maps all at once. Somehow, this is the nature of Hodge-Lefschetz and Hodge-Riemann relations that are found in nature. They always come in families. So let me illustrate this extra part. So the existence of injective map is just equivalent to the statement of the conjecture saying that one number is larger than the other. But the extra requirement is really saying something about the structure of this linear algebraic process. For example, if you think of a set of injective maps between 3-element sets and 3-element sets, then in general there are 6 possibilities. 3 factorial is 6. But for example, if you are looking at some instance relations that are shown in the left part of the picture, and you require that your injective map preserves that instance relation, then out of these 6 injective maps, only 2 survives. These are called matchings. So there are 2 matchings for this instance. But if your incidence between 3 and 3-element sets looks like that, the one on the right, then you see that although there are 6 injective maps, but none of them can preserve the instance relation. So this preserving this instance relation is a combinatorial analog of this multiplicative structure of the cohomology ring of the projective varieties, for example. And as you can see, this is a statement about linear algebra. So you give me a collection of vectors, I produce these sets, and ask whether there is an injective map from one to the other, or just the cardinality of one set is smaller than the other. But this linear algebraic statement currently has no combinatorial or elementary proof. So the case of matroids that I'm going to introduce later, which somehow corresponds to non-realizable configurations, remains open. The same is conjectured to be true, but we don't know how to prove them for these non-realizable configurations. And we don't know how to prove the same statement for this abstract configuration because the current proof uses the decomposition theorem and the Hodge-Lefschetz theorem for L-adic perverse sheaves of Bailins and Bernstein, Deligne-Gauber. So this is some deep statement that algebraic geometers have worked hard to prove it. And right now, even for this linear algebraic statement, without this decomposition theorem package, we don't know how to produce such an injective map between these 2 finite sets. So one combinatorial challenge will be to prove this without using decomposition theorem and Hart-Lefschetz theorem. And later I'm going to show you a combinatorial statement which I would call the Hart-Lefschetz theorem in this setting, which would imply this theorem without using the decomposition theorem package. So this is a combinatorial shadow of the Hart-Lefschetz theorem. So let me now turn to the Hodge-Riemann relations. Again, without telling you what actual Hodge-Riemann relation is, but its shadow can be already formulated purely at this undergrad linear algebra level. But again, the assertions will be quite non-trivial, I think. So let me not be shy and just define the object that I'm going to deal with. So this is the abstract combinatorial structures that I believe satisfy Hart-Lefschetz and Hodge-Riemann. So I'm going to define a matroid M as some finite structure defined on the ground finite set E. So this E will be the same E that we have used before. So it is by definition a non-empty collection B of subsets of E that satisfies the basis exchange axiom that we are familiar in linear algebra. So the members of this family B are called bases of my matroid. And basis should satisfy this property, which says that if you have any two distinct bases, B1 and B2, and if you have any element, say x1, in one of the bases but not in the other basis, then you can always find the element in the other basis B2, not in the first basis B1, so that if you replace x1 in the first basis by x2, then it's again a basis. And we all know that this is true if I start from a vector configuration and declare basis to be the basis in linear algebra sense, then you can do this. So one consequence of this defining axiom is that any two bases of my matroid have the same cardinality. Because if you give me any two bases, I can move gradually toward from one basis to the other basis, exchanging one element at a time, and eventually arriving at the second basis. So this common cardinality of any basis is called the rank of a matroid, corresponding to the dimension of the vector space. So if you have never seen the definition of matroid, it's not so easy to come up with non-trivial examples of matroids. Maybe except for the ones that comes from vector configuration. So let me just tell you three important classes of matroids, maybe the only three important classes of matroids that we should keep in mind as running examples. So one way to construct interesting matroids is start from a connected graph. And in this case, we take this ground set E to be the set of all edges of my graph. And the collection of bases will be the collection of spanning trees of G. So the maximal trees contained in my graphs. And then you can check that it satisfies this basis exchange axiom. So we have a matroid associated to any graph. And the second example is coming from linear algebra, where you start from any vector space or some field, and you take E to be some finite spanning subset of my vector space, and you take basis to be the collection of bases in the linear algebra sense. Then we again have a matroid because we know that these bases satisfy the exchange axioms. And the third most important class of matroid is the matroids consists of all classes not from 1 and 2. So, and the most important thing about the third class of matroid is that they exist. And it was recently proved that if you count all matroids according to their size, almost all matroids belongs to class 3. So if you're making a statement about matroids and maybe using some fancy tools from algebraic geometry to prove the statement for matroids coming from some field, coming from some choice of vector space over some field in degree 2, then you have proved the 0% of the assertions that you are hoping it to be true. This is our case now. But the one important reason why people introduce this notion of matroids is that forgetting about the class 3, if you just care about classes 1 and 2, is that if you think about combinatorial statement in terms of matroid language, it nicely combines statements from the first world and the second world. So sometimes you can have intuition about vector configuration by thinking about graphs and vice versa. So there's a famous saying by the graph theorist Foto, who says that if a theorem about graphs can be expressed in terms of edges and circuits only, it probably exemplifies a more general theorem about matroids. So you can conveniently transplant your graph theory intuition to linear algebraic situation.
Deliberately you separate 1 and 2? I mean, 1 and 2 basically.
Yeah, that's right. 1 is a subset of 2. So given any graph, you can carefully construct a vector configuration whose linear independence exactly captures this dependence given by circuits of my graph. So that's another thing that we should keep in mind. Yeah. So let me try to tell you this Hodge-Riemann relation from the point of view of this phenomenon of negative correlation in graphs. So let's think of a connected graph and think of a randomly chosen spanning tree. So let's say you pick uniformly at random of some spanning tree of your connected graph. And then you compare the probability that a given edge I is contained in this random spanning tree with the conditional probability that I is contained in this random spanning tree, given that it contains some other given edge j. And it turns out that, and this is a non-trivial fact, that for any distinct edges I and j in my connected graph, one probability is always larger than the other. So the presence of one edge makes the presence of any other edge in a random spanning tree less likely. And this sounds like a reasonable statement if you already occupied a place in a spanning tree by one of the edges, and the other edges can have only limited places to go. But this is to make this sort of intuition precise requires some work. So we say that pairs of edges in connected graph are negatively correlated from the point of view of spanning trees. So they repulse each other. If it contains one, it does not want to contain the other. But in simple terms, this is just one numerical inequality. It just says that for any distinct edges I and j in any given connected graph, you always have this inequality where bi over b is at least as large as bij over bj, where bi is the number of spanning trees that contain I, and b is the total number of spanning trees, and bij is the number of spanning trees that both contain I and j, and bj is same for bi. So this is one of those statements. It's a statement that is universally true for all connected graphs, and it only involves edges and bases, spanning trees. So according to Tut's instruction, we should try to see whether this is actually true for vector configurations also, or maybe for arbitrary matroid. Certainly, we can formulate the same question for arbitrary vector configuration. You give me a spanning vector configuration, and I randomly choose a basis contained in that vector configuration. And I can define these numbers. Bi is the number of bases that contain a given vector I, and bij is number of bases that contain both I and j, and so on. And we just ask whether one number is larger than the other number. So people actually, at some point in history, believed that this must be true for all vector configurations or maybe for arbitrary matroid, and they succeeded in proving this negative correlation phenomenon for matroids which are realizable for every field. This covers the case of graphs. But sometime in the 70s, Seymour and Welsh found a particular vector configuration which are only realizable over fields of characteristic 2, which has this ratio, b times bij divided by pi times bj, which is supposed to be at most 1 if negative correlation is true, is actually more than 1. It's something like 1.02 something. So this is somewhat weird from the graph theoretic intuition. There is a vector configuration where two vectors are attracting each other from the point of view of a random basis. And this doesn't happen very often. It's a safe bet that if you start with your favorite vector configuration, then you will most likely see a negative correlation phenomenon. But if you carefully choose certain vector configurations which are realizable over some fields only, then you can sometimes make this ratio go above 1. So let me propose to define this, this invariant of a field. So you give me a field, let's say K, and I will define the correlation constant of field, that K, as the supremum of this ratio, b times bij divided by bi times bj, over all pairs of distinct vectors I and j in every possible finite vector configuration in every vector space over K. I hope the definition is clear. So there are many vector spaces over the given field K, and each vector space contains many possible finite vector configurations, and each configuration, I take the supremum of this ratio over all possible pairs of this. So it measures how strongly two pairs of vectors can attract in possible vector configurations over that field. So what is not clear is that this is well defined. It's not clear whether this ratio has an upper bound because we are taking supremum over huge collection of things, all possible vector configurations in all dimensions. And the finiteness of this correlation constant is one of the elementary consequences of the Hodge-Riemann relations for finite geometries that I'm going to introduce. So again, this is a completely elementary linear algebraic statement, but I don't see a good way to justify the finiteness without making use of this point of view given by the Hodge-Riemann relation. So actually what you can prove is that the correlation constant of any field is at most 2. So given any field, the correlation constant is some number in between 1 and 2. And I don't know how to compute this invariant for any field, but I think it may be a very interesting invariant. So let me, how to justify a statement like this. This is a universal statement on linear algebra. So actually the statement will be valid for any matroid. So say you have a matroid on n element set, 1 for n, and I'm going to define an n by n matrix, say Bm, by saying that ij entry is 0 if I equals j, so long zeros on the diagonal. And non-diagonal entries are bij, where it's the same bij, number of bases containing both I and j. So this is a symmetric matrix associated to any matroid. And I'll suppose that MS rank at least 2, which means that this matrix is not 0. So it's not a serious thing. And what we can prove is that for any matroid M, this symmetric matrix has exactly one positive eigenvalue. And this is the first non-trivial piece of the Hodge-Riemann relation you can formulate in general for arbitrary matroid. And I don't know an extremely simple proof of this purely combinatorial fact. So you can prove this using pure combinatorics, but the current proof that I know is rather long and tedious. And in addition, I do not know how to prove the Hodge-Riemann relations for M in higher degrees. So even if you're starting with the matroid that are coming from a vector configuration, say over finite fields, you can formulate Hodge-Riemann relation in any degree, but we don't know how to prove it. Using algebraic geometric tools or not. It's simply not known. So let me just show you some examples to tell you how concrete the statement that I'm talking about is. So let's say you have a matroid on the complete graph on 3 vertices. And then you're counting spanning trees containing various pairs of edges. So in this case, our matrix B is extremely simple. So there's zeros on the diagonal as always. And for every pair of distinct edges, there is exactly one spanning tree containing both, namely itself. So all the other entries are 1. And it turns out that the eigenvalues of B is 2 and -1 and -1. So there is exactly one positive eigenvalue. If you start from a complete graph on 4 vertices, now the matrix is more interesting because the number Bij now depends on which pair of points, pair of edges that you have chosen. There are essentially 2 distinct cases. If you choose 2 edges that are adjacent to each other, then one of the remaining 4 edges does not form a cycle with the pair of edges, so it does not form a spanning tree. So the number is 3. On the other hand, if you pick 2 edges that are disjoint from each other, then you can form a spanning tree by adding any one of the remaining 4 edges. So the matrix is this. So some entries are 3, some other entries are 4. And the Hodge-Riemann relations will say that it has exactly one positive eigenvalue. And it turns out that the eigenvalues are 16, and you cannot really see it, but it's -2, -2, -4, -4, -4.
The difficult part here is uniqueness, right? Because
That's right. It has exactly one positive eigenvalue. There will always be at least one positive eigenvalue. Yeah. All the others will be negative, and if you are assuming a simple graph or a simple matroid, there will be no 0 eigenvalue. So other will be non-singular and exactly one positive eigenvalue. So let me try to convince you to show you, tell you some sort of feeling what kind of information is contained in a statement like this. So let's look at our matrix as a symmetric bilinear form on Rn, where Rn is equipped with this distinguished basis, EI. And I'm going to restrict this bilinear form to the 3-dimensional subspace spanned by EI, the standard basis vector, and EJ, another one, and the sum of all these standard basis vectors. Then I get a 3x3 matrix just by restricting. And we can write down this 3x3 matrix in terms of our numbers Bij, if we want. But then you can apply this standard linear algebraic trick, this Cauchy eigenvalue interlacing theorem, which tells you that if you delete rows and columns from symmetric matrix, then the new eigenvalues interlace the previous eigenvalues, to conclude that the smaller 3x3 matrix also has exactly one positive eigenvalue. And there are some cases where it's 0, but not important. If you believe that the original matrix has exactly one positive eigenvalue. But this is a 3 by 3 matrix, so we can, if we want, we can write down all its entries in terms of bij's, and if we want, we can write down the determinant of it, for example. And exactly one positive eigenvalue condition will say that the determinant will be non-negative. So the eigenvalues are either plus, minus, minus, or plus 0 something. In any case, determinant is non-negative. And you can write this fact. So if you express the determinant of this 3 by 3 matrix bij, then you get the expression which says that this b times bij divided by bi times bj is bounded above by 2 minus 2 rank inverse. So in particular, this ratio is always strictly bounded above by 2. And therefore, the correlation constant of any field is at most 2. So, and this is, so I try to guess what the correlation constant may actually be for some simple fields like Z mod 2Z or Q. And I could not come up with a reasonable guess. So it's, for every field, it's some number between 1 and 2. And it appears that if you start from small finite fields, you get some large number. So you can, the current record for Z mod 2Z is something like 1.17 something. And then it seems that the correlation constant drops little by little. And then at the very infinity where you have characteristic zero fields like Q and Q bar or C, then it's the smallest. But we don't know anything at the moment. But this experimental fact that apparently configuration over finite fields achieves higher correlation constant suggests that it may be more delicate to prove the Hodge-Riemann relation, higher Hodge-Riemann relations in over finite fields. So I'll get that to later. So let me now end by showing you, or at least giving you some hints of the actual Lefschetz and Hodge-Riemann relations in linear algebra or for any matroid. So just like the other Lefschetz theorems, it will be a statement about some algebra. And the algebra is produced by any matroid, say of rank D, and constructed from its collection of its flats. So in the linear algebraic setting, this L is our previous L, which consists of all subspaces spanned by subsets of my vector configuration. So this is a graded poset. And out of this poset, you can construct a cohomology-like objects. So I simply construct a Q vector space with bases corresponding to each one of the flats in my matroid, subspaces. And I grade it by the dimension of the subspaces. So let me call this graded vector space B. And now I define the multiplication by saying that the product of two flats, y1 and y2, is either 0 or the span of y1 and y2, if I view them as subspaces. It is the span if the dimension of each subspaces add to the dimension of the span, so it corresponds to the geometry condition that the two subspaces intersect only at 0, and otherwise it's 0. In this way, you can make this graded vector space into a graded algebra. It's a graded commutative algebra defined over Q, and it's a graded version of the Möbius algebra for this poset. And this poset is equipped with a family of Lefschetz elements. But let me just, to simplify, just choose one of them. So one of them is what I call L, and it is the sum of all elements in L1. So it's the sum of all degree 1 subspaces. And conjecturally, we should have the following version of Lefschetz. So for every p, which is at most d½ the repeated multiplication of L, going from degree p piece to degree d minus p, should be injective. So this statement immediately implies the conjecture on the cardinality of rank k-flats and co-rank k-flats, because the dimension of the vector spaces are simply the number of subspaces of dimension p and number of subspaces of codimension p. And this statement is in fact true when n is realizable over some field, and this is where all this decomposition theorem and Hodge-Lefschetz comes in. So what happens in the geometric situation is that you can use decomposition theorem to show that this B, algebra B, is actually the singular cohomology ring of some projective variety. And this projective variety has very nice property, which says that this singular cohomology ring embeds into its intersection cohomology ring. Usually there is a some kernel if you want to map a singular cohomology to intersection cohomology. But this is actually, so this B is actually a submodule of the intersection cohomology. And by another V theorem, we know that intersection cohomology satisfies Hodge-Lefschetz, therefore any of sub-object satisfies the, should inherit this injectivity part of the Hodge-Lefschetz. But another remarkable fact is that, I mean, from the geometric viewpoint, is that I can define this algebra B over using coefficients Q. I mean, you can start with the vector configuration over finite fields, but this thing, algebra, I can always construct it over Q. This is in sharp contrast to what happens for the cohomology of projective varieties defined over, say, finite fields. So for various reasons, we cannot simply construct the analog of the singular cohomology for those varieties using Q coefficients. So, and people instead use QL coefficients. I mean, that's fine for the purpose of the Hodge-Lefschetz theorem, but if you start using fields like QL, which has characteristic 0 but is not ordered, then you cannot make sense of the Hodge-Riemann relations, which predicts that something is positive. So positivity is entirely gone if you use QL coefficients, but these objects you can construct using Q coefficients, and you can formulate Hodge-Riemann relations. And this is partly because every cycle in the geometric setting comes from algebraic ones. So B entirely consists of algebraic cycles. So for any matroid M, you can define at least a natural graded B module, the same B, which contains B that satisfies Poincare duality and conjecturally Hodge-Lefschetz. And if n is furthermore realizable over the complex numbers, for example, or any field of characteristic 0, this module that I have in mind, which has a purely combinatorial definition, also satisfies the Hodge-Riemann relation, which says that the Hodge-Riemann form on the primitive cohomology is positive definite, using the known fact in geometry. But even in the realizable case, where you can realize your matroid by vector configuration over finite fields, the Hodge-Riemann relation is not known there, because this user of this Arabic perverse shapes thing only works with this QL coefficient, and you cannot really even formulate the Hodge-Riemann relation. And the formulation for this algebraic part of this cohomology rings is the topic of the standard conjectures of Grothendieck on algebraic cycles. And according to this philosophy, you should always also have this Hodge-Riemann relation for any vector configuration, maybe even for finite fields. But even this linear algebraic statement that you can really write down, given enough time, is not known. So I personally believe that Grothendieck standard conjectures are true for any field. But if you're a disbeliever, this is a very nice place to experiment and see if the prediction is really correct. Because this Hodge-Riemann relation is an extremely delicate statement. It says that some symmetric matrix has exactly 16 positive eigenvalues and 135 negative eigenvalues and something like this. So unless there is a really good reason for it to be true, it will be probably false. But even in this linear algebraic case, for example, you can write down a program and see whether Grothendieck's prediction is true, and this is already the new and non-trivial cases of the standard conjectures. So I hope I convinced you that even in this linear algebra world, there are many cohomological statements that we do not really understand very well. And I'm having really very much fun in playing with this sort of statements, and I hope you at some point will join in having this fun together. So I'll stop here. Yeah.
Questions and comments?
I have two questions. The first, you mentioned an example that achieves a correlation constant of about 1 or 2 something.
Yes.
Is that the highest correlation constant that is known, or are there?
So the question was that this correlation constant, at least being as large as 1.02, as was shown by Seymour and Welsh, was still the record. And the answer is not. So Ben Schroeder at Berlin has run some computer programs and did some search, and the current record for characteristic 2 fields is 1.17. So the correlation constant is at least as large as that. On the other hand, the record for fields like Q or even C is somewhat lower. It's like 1.06 or 1.07 something. That's the lower bound that we know now.
And the other question is, I'm thinking you take like a vector space
and you think like the subsets of n vectors that span a d-dimensional vector space that can be realized as a locally closed subset of some affine space. And what happens if you try to make like a filtration of those sets? Say you take the sets that achieve a correlation constant of at least lambda, and you move the lambda, and you get like some kind of filtration. Do you know anything about that?
I don't understand the question, which probably means that the question is not so easy. So maybe we'll discuss it later. Yeah.
Any other question?
A deep generalization of this hard Lefschetz and Riemann-Hodge, is there a version which goes over into intersection cohomology or into mixed Hodge structures?
So this even in this linear algebraic setting, the corresponding geometric picture is on the intersection cohomology. So this you can already guess from the statement of the theorems. So the number of p-dimensional spaces is at most codimension p spaces. So one is always larger than the other, and they can be really different. So if you are expecting the full hard Lefschetz, you expect that something is bijective to something else in complementary degree. But the difference comes from the singularities, because I'm only looking at the part that comes from the singular cohomology, which embeds into the intersection cohomology as a proper subspace. You inherit the injectivity part of the hard Lefschetz statement, but not the bijectivity part. So the fact that 4 points in plane determine 6 lines and not 4 lines shows you that there is some singularity behind the picture. But I cannot strictly say that this is intersection cohomology because I'm doing everything with Q coefficients. So I'm doing something like intersection cohomology using only algebraic cycles.
So another question, I am really surprised that inside the proof, as you mentioned, you need to use this very deep theorem, this is the composition theorem of Bernstein, Beilinson, Delin, and Gabor. And so, could you say some words where, I mean, how come this deep theorem appears in this elementary setting?
So
In an easy way?
you have a finite vector configuration, and using this you can construct some projective variety with interesting singularities. And it is known by these deep theorems that the intersection cohomology with QL coefficient satisfies a Hart-Lefschetz theorem. And using the decomposition theorem, you can show that this combinatorial algebra B embeds into the intersection cohomology after you change coefficients to QL.
Do you need a ladder cohomology, or you could do it for the complex numbers?
So if I have a matroid which are only realizable with, say, characteristic 2, I really have to do L-adic cohomology. So that's why we don't know Hodge-Riemann relations even in those realizable cases.
Seems there is one more question, please.
Yeah, so I'm interested so to know if this naturally graded algebra that you develop behaves in some way naturally with respect to specializations of matroids. And if they do they define an object over the so-called Macphersonian, for example, out of which your theorems could say something about the homotopy type of the Macphersonian? You know, there's a long history behind that, right? So.
Yeah, I mean, so you can think of this B's as somehow attached to every possible matrix, and the collection of all matrices forms some sort of a combinatorial spaces. Mm-hmm. And this attaching is somehow so functorial. So it's just like attaching the cohomology ring to projective varieties, and there are also this natural maps corresponding to pullbacks and push forward. And this may be the first step to take if you want to prove Hart-Lefschetz and Hodge-Riemann. So there is a combinatorial category associated to every matroid which resembles the category of perverse sheaves, for example, and they all are related to each other in a nice way. And even in non-realizable cases, you will all have this functoriality. And the question is whether the main conclusions in the geometric setting are still true in this more general setting. And we don't know.
Any other question? Comment? So, thank you, June, again. So, the morning session is over. We meet together this afternoon at the Institute of Math.